Hey, so in this video, we're going to be looking at probability trees again. We're going to be looking at what I like to call yes-no trees. And there'll be an obvious reason as to why I call them yes-no trees in a bit. But we're going to be continuing some of the ideas that we had when we looked at probability trees in a previous video. Thinking about what combinations of events we need. Do we need to look at multiple branches of our tree? Do we need to add some things together? What do we need to multiply? All of these kinds of questions we will still be thinking about. But you'll see that if we were to do the questions that we're going to look at today in the way that we did them before, they would get rather out of hand rather quickly. Okay, so let's have a look at these. And we're going to start off with the problem that we looked at last time, just to familiarize ourselves. Okay. So this is one of the kind of staple problems that we looked at last time, where we've got colored beads that are in a bag and they are two different colors, black or green. We take a bead at random from the bag, we look at the color and put it back. We then choose a second bead. Okay. Now the probability tree itself is not too bad for this because it only consists of two options, black or green. And because we pick the bead up and put it down in this bag when we're done, the probabilities don't change from the first pick to the second pick. They remain the same. So when we come to look at the different branches that we want to look at a black on the first choice and a black on the second choice, we just multiply those two branches together because we're thinking black and black. And is a keyword for us to multiply, or is a keyword for us to add. Okay, so if I'm thinking green and black in that order, I would want to go 5/9 times 4/9 to give us 21/80. Okay. If I was looking at two beads the same color, I could have black and black, 4/9 times 4/9, green and green, 5/9 times 5/9, and because I could have black and black or green and green, I could add those two bits together. Okay. Now, that technique for this kind of a question is ideal. It works, it's quick, it's efficient, and yeah, we end up looking at the correct answers. But what we will see for the types of problems that we got coming up now is that this becomes far less efficient. Okay, so in a bag we have different color marbles. 3 are blue, 4 are red, 2 are yellow, 1 is gold, and 2 are of this kind of murky brown color. And a marble is picked blindly, replaced, and then we have another go. What is the probability that 2 picks are required to get the gold? Okay, now if we did a probability tree in the sense that we've done them before, that would quickly get to a point where it is just out of hand. This is just the first pick. That's nonsense. Okay, because now from here we would have to have a second branch going from blue, 1, 2, 3, 4, 5 from blue, 5 from red, and it just gets out of hand. It's absolutely insane to think about doing it this way. Okay, so instead we want to improve this. We want to think, how can we improve this? And the key is us thinking about yes or no. What do we actually want? We want the probability that 2 picks are required to get the gold. The gold one in this case is our success. That's our yes. The no is everything else. Okay, so if we were to split this down into 2 categories to make this a lot easier for ourselves, we could have yes, we get a gold, no, we do not get a gold. Okay, And that is what we see here. We get our first choice, where we get something which is a gold. That's our yes. And we get something which is not a gold. That's our no. And then when it comes to our second branch, we get gold again or not gold. Gold or not gold. Okay? And it takes this insanity and reduces it down to something which is way more manageable, something which is much more in line with how we have been thinking about probability trees before. Okay? So, we're going to take this problem that we've got here, just going to flick it onto a new slide, and we're going to look at this from start to finish so we can see just how this ends up working. Now, if you wanted to, if you think, actually, I understood what we were doing in our last video, you could very well pause the video here, have a go at this question, and see how you do, okay? So, this is me going to go through it now. I've got 3 blue, 4 red, 2 yellow, 1 gold, and 2 murky brown. Okay, so 3 plus 4, 7, plus 2 is 9, plus 1 is 10, plus 2 is 12. So I've got 12 in total. So that's going to be the denominator of our fractions for the probabilities. Okay, so if I'm going to fill in these probabilities, one of them is gold. That's 1 out of 12. The things that are not gold are everything else, which is the 11 out of 12. Now the marble is picked and then replaced, so that means that the probabilities in our second choice are not affected by the probabilities in our first choice. They are independent of one another. So that's what our probabilities will look like. Got 1/12, 11/12. Both branches add up to make 1. Okay, they're mutually exclusive. They cannot happen at the same time. So now we want a particular scenario of this. We want the probability that 2 picks are required to get the gold. So that means that we don't get a gold on our first chance. That's this one here. And then we do get a gold on our second chance, which is this branch here. And hopefully you remember, if we go across 2 branches, we need to multiply. So we want the probability of not gold and then gold. So 11 out of 12 times by 1 out of 12, which is 11 out of 144, which is less than 10%. That's not a lot of wiggle room for us. Okay. Now, for a little bonus question, we could say, well, what's the probability of getting 1 gold? Okay. Well, the probability of us getting 1 gold, this thing here, would be the probability of us getting a gold and a not gold plus a not gold and then a gold. Okay, doesn't mention anything about order. Okay, so we have to look at both scenarios. Okay, gold, then not gold, and gold, and add them together. Okay, so 11 out of 144 plus another 11 out of 144 is 22 out of 144, or 11 out of 72. Simplify your fractions wherever you can. If you can't, leave them as they are. So, I'm going to give you another one to have a look at now, okay? And I'm going to have to explain a couple of things just in case you've never heard of some of these things before. Okay? So, a D20 is a dice that has 20 sides, okay? So, a D20 has the numbers that goes from 1 up to 20. Okay? Used a lot in some board games, okay? And we're saying that it's fair, so all of the probabilities are the same, okay? There's no bias involved. It's a fair dice. It gets rolled twice for a game of Dungeons and Dragons. The roll will be determined successful and a battle won if at any point a number greater than 17 is rolled. What is the probability of this only happening on the second throw, just for maximum tension? Okay. So the first thing you'll want to do is to think about what are the scenarios that we want to put into our tree diagram. Okay. So I'll give you a moment to have a think of that. Pause the video, try and draw a tree diagram. Feel free to resume the video when you've got one together. Okay, so we're going to reveal the tree diagram now. So our tree diagram is going to look like this. Now in this case, a success for us is a number that is greater than 17. Okay, a failure for us is something which is less than 17, or less than or equal to 17, I should say. Okay, so we want to think about what our probabilities are. In our second choice, I say second choice, it's more of our second roll, the probabilities will be the same, because rolling a dice one time doesn't affect what it gets on the second roll. Okay, they are independent events. So let's fill in our probabilities. The probability of us getting a success, something greater than 17, we've got 18, 19, and 20. So that's 3 possible things out of the 20 numbers that we have on a d20. Our failure, less than or equal to 17, well, there's 1 to 17, so there's 17 numbers. And the probabilities in our second roll are going to be the same as they are in the first roll. So now we want to know what is the probability of this only happening on the second throw for maximum tension. So the second throw means that it has to fail in the first one. So we're going to go down here and then over to our success on the second throw. So 17 out of 20 times by 3 over 20 will give us our probability. So 54 over 200. Okay, so what? That's going to be a little over a quarter. Okay. Which, is... I wouldn't say that's not bad, really, for getting something over 17. Now, a little bonus question here. When you, if you've got this kind of scenario in a board game, normally you don't aim to get it on the last go. You want it to happen as soon as possible. Okay? So we want to know what's the probability of us getting a roll which is greater than 17 at all, not just on the second throw. Okay, and for this we want to think carefully about what we want. So we also have this extra little thing here. If this happens on the first throw, you can stop rolling. Okay, well, I mean, you don't need to keep rolling. If you get something that's greater than 17, it's an automatic success. You can carry on. So for this thing here, we've got 2 things that we need to look at. We've got probability of us getting a success on the first throw, plus the probability of a success on the second throw. Okay. Because we've got 2 times that this could possibly happen, so we want to think about, well, what if it happens? Okay, success on the first throw, there should be 2 C's in success. There we go. Is just 3 over 20. Success on the second throw, 54 over 200. So combining those 2 things together gives us our overall answer. Okay, so that seems to increase our percentage quite considerably, really. 3 out of 20 plus 54 over 200 is the same as 30 out of 200 plus 54 over 200, which is 84 out of 200, which is actually same as 42%. So we go from just over a quarter to just over 42%, which is not a bad increase, really. Okay, so this is what I mean by a yes/no scenario. Okay, and most of the questions that you'll see on Hegarty will be things like this. Okay, you'll need to read the question carefully as to see what kind of question it's asking, and also think about carefully thinking about what your tree diagram is going to be looking like. What's your success? What's the thing that you want? What's your failure? What's the things that you don't want? Okay. Now, if you've grasped that reasonably well, and you think, yeah, I understood what was going on here, that was all right as well. I managed to do that. That's fine. I understood how to get my second throw success here. I've got an extra little problem for you. Okay. And it's coming up now. So now, in a similar game, similar scenario, we get to roll this dice 4 times. Not just twice. We get to roll this dice 4 times. Okay. So we have the same numbers. It's still a d20. We want to know the probability of this happening on the last throw. Okay. So this, in this case, just means our... Oh, hang on. Just means our 4th throw. Now, we want to think about success and failure. Okay, success, as we had in the previous diagram, is something which is greater than 17, so it's 3 out of 20. And a failure is something which is 17 out of 20. Now, we're saying that we're going to fail 3 times and then get a success on the last one. So I want you to think now, what calculation would you have to do in order to make that happen, so that we fail 3 times and then succeed on our last throw? Just going to give you a little moment just to think about that for yourself. Okay, hopefully you've had a little think. We want to fail 3 times. Failure is 17 out of 20, the numbers that are less than or equal to 17. A success is 3 out of 20, the numbers that are greater than 17. So if it was happening on the 4th throw, must have failed 3 times in a row, and then succeed on the 4th. So that's going to be 17 out of 20 to the power of 3. You know, that is just a shorthand of us saying 17 out of 20 times 17 out of 20 times 17 out of 20 times 3 out of 20. Okay? 0.092 as a probability, or 9.2%. So you've got approximately a 10% chance of nailing it on your last throw. Okay? Now, as we said before, we could get a success on any throw and we could just stop. Okay? So actually the probability of us getting it on our at all in this actually is not that bad. Okay? You could have a look at that if you were interested. What we've got here, though, is the first steps in what we would call probability with success and failure. And it's looked at in binomial distribution, which is something that you'd learn about in AS level statistics or AS level maths. Okay? Now, as just a quick summary of what we've looked at through here. Rather than going for absolutely mental looking probability trees, we should look to see how can we simplify them. What is the thing that we want? Does it change? If it doesn't change, we can simplify our trees significantly, okay, to something like what we've got here. When we simplify our trees, then finding the probabilities is just the same as we did before, okay, but we need to look carefully for the probabilities that we are looking for. What is the thing that we want? What is the thing that we don't want? Okay, you may need to add things up in order to get that probability of something that we don't want. As before as well, make sure that you look carefully to find out what you need to multiply together and if you need to add things together in order to get the probability that you're after. And as well, you can think of these in terms of a success and a failure. What is the thing that you want? What is the thing that you don't want? Just make sure that you read the question carefully so that you get the probabilities that you want and the probabilities that you're after. Okay? The Heggerty video may explain things slightly differently to the way I've done, so make sure that you watch that just in case you weren't sure about something that I said. Feel free to email me as well. If you're one of my students, I'll email back to you with some hints, tips and replies, or you can ask some questions of me in the video chat and I will answer them should they be kind of on topic. Okay? And that's it for this one. In the next video, we're going to be look at what we call dependent events. Okay, things which do impact one another. And we'll see that actually the techniques that we've been working with, they're still pretty good. So I'll see you in the next one. Take care. Stay safe.